Well, hello everyone, and welcome back to Adrian's Digital Basement. On a recent video on the main channel, I took a look at a Turbo XT clone, an NCC PC from 1988, and that machine ended up working after I replaced a few components inside that were bad. So for today's video, I'm going to be taking a look at those bad components. One of them was a Twinhead monochrome graphics or monochrome display adapter with a parallel port, and the other one was the 5¼ inch floppy drive. Both of these components are somewhat common in that you can easily find replacements of these on eBay. The thing is, these parts are getting more and more expensive, so it'd be nice to see if we can actually fix these things, especially the floppy drive, because these are becoming more rare. And if we can get these things working, then great. If not, it'll be a good learning experience. So without further ado, let's get to troubleshooting. Let's start by taking a look at the two components that need to be repaired. Now this card is both a monochrome display adapter and a printer interface card. And the printer interface portion of this card is going to be separate, even though it's all combined into one card, and we really don't need to concern ourselves with trying to get that part of the card working. I don't know much about this card other than it has 64 kilobytes of DRAM on it. And that implies that this is Hercules graphics compatible. So it's not just regular MDA or IBM MDA compatible. Actually has some high-res 1 bit per pixel video mode that is possible with it. The UM82C11, this has to do with the printer port. We can totally ignore that and anything that it's connected to. I wonder what's under this label. Let's scratch this off. This label, which indicates this is from 1987, 11th week, is being a bit stubborn. So we need to heat it up a little bit so I can get this off more easily. Awesome. This is just a regular 6845 CRT controller, so I have plenty of these in case this is the fault. So really the biggest concern is this Twinhead IC, which almost certainly combines a bunch of other logic ICs that were on the original Hercules card, and whatever's under this label here. This is a PAL or Programmable Array Logic 16R8. Typically these will be used on cards like this for chip select, aka it is mapping the video memory into the actual physical memory space of the motherboard you have it plugged into, and probably, well, it could be also handling the parallel port chip select. And this is the other component we're going to be looking at. It's a 360K floppy drive. All I knew is that this thing seemed to be selectable, so the computer would try to read from it and the LED would turn on, but it seemed that the spindle was running slow and it wasn't reading anything. With devices like this, of course, you could have mechanical problems and you could have electronics problems. And the note I had said it was spinning slowly, so that could be a problem with the speed controller on the bottom board, but we could also have issues with the mechanics of the clamp where it holds the disc. Maybe the disc was slipping. There could be all sorts of other issues with the electronics. There's just all sorts of things that can go wrong with these drives, but I would like to get this fixed because, like I said, 360K drives don't grow on trees. So I think the first thing we're going to do in this video is look at this monochrome video card. For doing the diagnosis of this, I'll be using this Pentium motherboard. It's a Pentium 166, and I've set this up for bench testing. And essentially there's a compact flash card. The fan is hardwired in because I like to be able to unplug and replug the motherboard very easily. I also have a speaker permanently attached as well, and a reset switch and a power LED. It's all the stuff that's good for having this on the bench. All I have to do is connect the power up, turn this on, and there you go. It will work. Now what I've been using lately for diagnosing and trying to fix ISA cards is a riser. I took this out of an old dead PC and you plop this into the motherboard and I can plug the card under test onto this side of the riser so I can see the top side of it and also record it with the bench camera, but easily probe it. Or there's an ISA connector there and I can get this on the back side as well. So it's great if I need to test signals on traces and things that are underneath ICs while the board is running. Now, what I always recommend before you start a process like this is make sure your test setup is working. So this is a CGA/monochrome card, and I have it set to MDA, that little toggle switch there. I'm going to plug this in. I'm going to connect this board up to my capture device, which happens to be the RGB to HDMI. I'm going to add a post analyzer card just to make sure the system is booting with this card connected up. This is a known good card, but I just want to see it all work. And I'm going to power this up, and we're getting normal post codes. Hopefully we're going to get a normal screen. Yes, there it is. It's a little offset, but that's just a setting in the RGB to HDMI that I can adjust to fix that. So tire capture settings working. Let's switch over to the Twinhead card. Now the reason for the post card is I want to make sure that when this is plugged in, that the motherboard is happy that it sees a video card. Typical modern BIOSes like this Pentium BIOS needs to see a video card or the system won't post all the way, or it'll give us beep codes. Let's turn this on without a video card and let's see what it does. I'm assuming it's gonna beep and be unhappy. There we go. So like long and a few short beeps. I think the system is actually working. It will boot up at this point. If we push F1 maybe. Let's see, I can probably get this to boot. It probably has an error on screen, like video card error. There we go. FF implies the system is fully booted and it's in DOS. That's exactly what it was doing when this card was installed. We just didn't have that long beep code, we just had a single beep. So what we need to see is, while this card is installed, is the system still booting normally? My recollection from when I tested this in the NCC PC is that when I turned on the system, all we got was a gray screen solid immediately out of this card, which implies there's something wrong on the output stage. What we need to know is if there's more problems with it and the system is not posting properly with this installed. Okay, here we go. 3, 2, 1. See what this thing does. Well, so we didn't get any beep codes, but at the same time, the card is stuck, or it's causing the system to be stuck. And that kind of implies, unfortunately, that there might be more wrong with this card than we can easily fix. I'm going to push the reset button. See, the light turns on. That's the reset light. When I let go, it's going to reboot again. And let's see if it gets stuck at exactly the same point. Yes, it did. D, hex D is the postcode. Now, I find this kind of strange, actually, because you would think that with the card malfunctioning, it just would behave as if there was no card at all.
Remember what I just said here. It'll become very, very important later.
And I'm tempted to remove this PAL IC, and let's see what that changes on the system. I'm kind of assuming now it's just going to think there's no card installed at all, but maybe it won't. Aha, stuck in exactly the same way. Interesting. Now what you see below my face is the output of the card. So if I turn off the system, you notice it goes blank or black. We turn it back on and it goes all white. And let's see what happens when I push the reset button. You'll see the reset light turn on. No change. Now this may be normal behavior for a card like this. It could be that the way that the card is designed, that it drives the video signal output of the card up to 5 volts before the card initializes. And it is the BIOS that's responsible for initializing the registers in the 6845 CRTC and getting the card actually running. Now, one thing that's actually possible with an MDA card is you can have both an MDA card and a CGA card installed at the same time. I'm going to switch this to CGA card mode, and I still can't get that in. I tried to move this over one slot to move it one more slot over. So let's see if the system boots okay with this CGA card installed and the MDA card. If both these cards are working, you can actually run dual monitor with a monochrome and a CGA card. And as long as the software using it is designed to talk to both cards, like write to the memory buffer on both cards and initialize both cards, you will actually be able to use both at the same time. So let's see what happens when we turn on the system now. Okay, so the flashing that it's doing is normal for the CGA card. I'm gonna pop the monochrome card out first. Let's just make sure the CGA card's working properly. I think it's in the wrong mode. Okay, I'm just switching it to CGA mode. Okay, there it is, the system is working. That flashing we saw is very typical with this card when you first power up the system. I'm just gonna demonstrate that by turning it off and on. So flashing, sorry about the flashing if you don't like flashing, happens a little while until the BIOS initializes the card. There it is, it's working now. All right, so the monochrome card is back in. Does the system initialize properly? It will flash until the system initializes the card. And it looks like the system is totally frozen again. Let's pop in the post analyzer. So it is frozen at exactly the same point. So it really feels like this card is causing the entire ISA bus not to work, which causes the whole computer to not work as well. So it seems like we have some pretty fundamental issues with this card that we're gonna have to diagnose before we can even go any further. Now, if we had schematics, it would make things a lot easier, but we don't. So we're gonna have to kind of figure out how things work. And I think what we need to do is start by looking at the signals that come across the ISA bus and what they're connected to. So on the back side, not a whole lot is connected. I think we have like a ground plane there, probably 5 volts. There's ground as well. I think that's 5 volts. So those 2 pins, and then I'm not sure what that middle pin is. We'll have to go take a look at that. And this side of the board, we have quite a bit more connected. Now, there are no schematics, of course, for this, right? So that's why we're just gonna have to muddle our way through and try to figure things out. So I have this ISA prototype board that happens to have all the pins labeled, and this side of the board is the equivalent of the component side of the board below us. Now, these pins here, the traces actually go up around to this side. So address line 0 all the way through address line 19, and data line 0 through data line 7. And these pins here will be those data lines. It looks like they go directly to this 74LS245. So let's double check that these are going to this IC. There's data line 7, 6, 5, 4, and so on. Okay, so the data lines are going directly to this. Now, when it comes to the address lines, which we know are on this side of the board, we're gonna have to figure out where they go. And I see that address line 0 goes to a via there, flipping it over, it goes to another via. So it's making its way totally somewhere else. So I'm gonna use this special probe that a viewer sent in. It's kind of got like a metal brush on the end. It's very, very handy for this exact use case. Because what I can do is I can brush around the board looking for where those lines are going. All right, so address line 0, at least it's making its way over to this side of the board, but it may go multiple places. So we have a 74LS125. I have to look up what that is in a second. But there's address line 0. Let's look at address line 1. See if it goes to a similar spot. Wow, it doesn't. So back to the brush probe again. All right, looks like address line 1 is going over to the 8211. That's the parallel port controller. And it looks like it goes to whatever this IC is. So it's probably going all over the board. So address line 1 looks like it goes to this IC. I'll put 2 dots on it for 1. Goes to this one as well. And address line 0 went up to this IC, 1/, and of course the data lines go to there. So I think our next step is to get this thing into the working system, and we need to scope those data lines while the system is not booting properly with this card installed. Because it's entirely possible, and it would be a very easy fix, if this LS245 is the chip that's died, and it's just trashing the entire ISA bus on the data lines. All right, I think we are ready for testing. I'm on one of the pins that I think would be one of the data lines, maybe data line 7 on the 74LS245. Okay, and we have activity. Whether that looks correct or not, it's hard to know. It's certainly kind of curvy. Let's look at all the various pins. I have to hit the reset button to get the system to kind of start again. It just freezes and stops running. Yeah, that looks same. Yeah, these all look the same, all the different lines. Now, interesting is there are occasional, like whatever this address line is, notice there is a nice square wave sometimes visible. Yeah, that looks a bit strange. What I need to do is swap to the other card, and we can take a look at what the signal should look like when we have a working video card. I'm just gonna try to probe right on the trace itself. All right, well, that certainly looks very similar, doesn't it? So I guess that's just normal for the ISA data bus. With that curvature you'll see on those waveforms, I would have thought it would just go straight up and down, kind of like the down to ground is pretty sharp and hard, but that rising up is a little sluggish. All right, well, what we do know for sure is the way this looks is normal, and this card is working fine like that. So this Twinhead card is not trashing the data bus. It looks identical, looks absolutely identical. So the pinout for the LS245 in this picture matches the exact orientation of the chip that's on the board. And the ISA bus itself is connected to the A side of this chip. So when this chip is enabled with the enable line low, pin 19, then whatever's on the A lines will go to the B lines. And then when you toggle the direction pin while the chip is still enabled, then it's the opposite. Whatever's on the B lines will be fed to the A lines. The A lines will drive the bus. That direction change should only happen when the computer is trying to read from the card itself. So I'm on pin 1, the direction pin. Let's just hit the reset button. So right now that is just high. What we need to do is take a look at the truth table for this chip just to make sure that that direction pin being high is normal. Actually, what we also need to do is check that it's being enabled. So I moved it up to a higher slot, so I'm on the enable pin. Let's power this on. This should be low when the chip is enabled, and it is. It's probably just enabled all the time, frankly. In other words, the pin 19 just might be tied to ground. And all it ever toggles on this chip is the direction pin anytime the card needs to be writing to the bus. If the CPU is trying to read from, say, the registers, although I don't think you can read from registers, but the parallel port can be read from, and also you can read and write to the DRAM that's on the board, the video RAM. Taking a look at the data sheet, anytime the chip is enabled, so that's the output enable or the enable signal we were looking at, that's low, and the direction pin is high, which is exactly how it is what we see on this card. That means the A data, which is the input, that's the ISA bus, is copied to the output of this chip that faces the rest of the card. So it's at least being signaled to work as expected for when this card is just being written to, which is normally what happens with a card like this, it's only written to. And if we probe one of the B pins, and I'm hitting reset, so that was the ISA bus being copied to the rest of this card. So I just need to make sure that all 7 of the data bus lines are copied properly to the rest of this card. Whatever pin this is, looks fine. Yes, all 7 data bits are being copied from the ISA bus to the card itself. So I think that chip is fine. And again, I'm just double checking the direction pin never changes. In fact, if we change this to normal triggering, and if we switch this to either direction triggering, if I hit the reset button and anytime the direction pin changes either low or high, it would cause it to actually capture that, and there's nothing. So it's kind of curious that the direction pin never gets toggled, and I would think it would because honestly the motherboard, you figure, would be reading and writing to the video memory to try to figure out if it's a monochrome or CGA card, because where the RAM exists in the address space on the PC is different for MDA versus CGA. That doesn't seem to be the case. And what we're taking a look at now is the enable pin. I just want to see if that line ever toggles, and it doesn't seem to. And I'm just going to check if the ground pin is connected to the enable pin. It's actually not. That would imply that enable pin is actually being driven by something on the board. So here is the curiosity about what's happening. We never see anything on this card ever trying to write back to the ISA bus. So it's not trashing the ISA bus. The ISA bus is fine, it's working okay. But yet putting this card into the machine causes it to kind of hang up with that postcode D. I should go look up what that D error code even is. Now, one thing that's unfortunate is the postcodes seem to change depending on like what generation of AMI BIOS you're using. And this is an AMI BIOS from, what year does it say? 1995. Oh, sorry, it's an Award BIOS, not AMI. So similar though, it depends on what version you're using. Award plug and play. It says PCI plug and play 586, 1995. Wow, it's absolutely pouring outside. Like hitting the window over there. Well, if this is right, measure the CPU for display, so it shows the 166 megahertz, which is what this is, and initialize the video. That's all happening with that error code D. And on this, B is plug and play initialization, verify the real-time clock, detect bad battery, blah, 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 does a bunch of stuff. I'm gonna put back in this known good card. I just wanna see what postcodes we're getting with this one. So it does the C stuff, then there's B, and then it goes whoop right past there. Let's reset the machine again. So yeah, it does a bunch of C stuff. So it starts at a higher number and then B. I saw a 3 for a second there. Let's flip the switch on this, switch it to CGA mode, see if it's any different. So B, 3. I swear I saw a D in there for a second, and then I assume that's the card getting initialized. Putting back in the Twinhead card. There's B, and then D. So this has me thinking, could the problem be that the motherboard is waiting for the card to talk back on the ISA bus, like to respond with something, and it never does? So we need to look at where the direction pin on the LS245 is coming from, because maybe that's the component that's bad, since that signal is always high. And if you recall, when I powered this up and we were looking at that signal, there was a little bit of activity on it. Maybe that was trying to drive it low, and it never did. So I'm on the direction pin, and I'm just using my normal probes here. I'm just curious if it's coming from this PAL, because if it is, that's potentially bad. No, it's not. I'm just gonna look physically to see where it's coming from. I can't see there. Oh, there it is. Okay, it goes there. And then that pin disappears underneath that IC. So going back to the brush again, Okay, there it is. There's the signal. It goes to this via, which probably goes on the other side of the board to that via, which goes to that pin there, the direction pin. So it's that pin. I'm just trying to see if it's going anywhere else. It's not on this side of the board. So it's the pin closest to the 6845. There it is, 74LS04. And it doesn't look like that goes anywhere else on the underside. It's hard to see exactly, but I don't think it does. I think that's an output. Let's look at the data sheet for the 74LS04. So 74LS04 is a hex inverter, and we're on the output. That's the output, and the input for that gate is this pin. Just put a little mark. So next step is just to check this signal with the oscilloscope, with the card running, just to see what that signal is doing, if it's changing or not. Okay, here we go. No. That signal is not changing either. So that would explain why the output just looks like that. So unfortunately, we have not found our smoking gun. I just have to kind of keep going backwards and looking for that signal. Now, this is where if we had schematics, this would be extremely helpful because I wouldn't need to do this whole searching process. I would just be able to look at the schematic and see exactly what's generating that signal. All right, with some searching around, it looks like the output that goes to the hex inverter there that actually generates that direction signal is this 74LS00, which is a NAND gate. Therefore, we need to take a look at the truth table for these two pins. It's a little hard to see, but yeah, so those two pins are the inputs. That is the output that goes to the other chip. So the output of this IC, when we looked at the scope, when we powered this up last time, was always low. And the only way you can get that is if both of the inputs are high. If either of the inputs is anything but high, then that will change to a high signal. So we need to just take a look at those signals, and they should be stuck high all the time. If they're not, then that chip is faulty. So first we'll start by taking a look at the output. There it is, it's low, stuck low. Okay, now we're on one of the two inputs, and it is high. And remember, what I said is if they're anything but high, then it's always gonna be low. So that looks normal. If I hit the reset button, there's a little bit of noise, but otherwise it's high. 4.4 volts, good enough. And the next pin over, same thing. So there's nothing to imply that this chip is the problem. We need to keep going. We need to keep going back. So just for fun, and maybe this would help us, I want to take a look at the data sheet for the IBM MDA adapter that has video, MDA, and parallel port. So similar to this. Now the D0 through D7, that's the data lines that come from the ISA slot connector, and it goes to a LS245, so very similar to this card. And there's our direction and G or enable pin. Let's take a look at where the direction pin goes. So it goes to an LS00. Now it's going to a hex inverter on this card first, and then an LS00. Now one of the lines going into the NAND gate is coming directly from MEM-R, which I'm pretty sure is the ISA bus itself. And the other one goes to the LS32, which goes to IOR and address enable. All on sheet 1. Let's take a look at sheet 1. And pretty much everything that's on sheet 1 is the ISA bus connector. So IO read, which will be for the parallel port, and mem read is for the memory read. That's definitely the ISA slot. But the address enable, that says sheet 1. Did we see that on sheet 1? I don't think that's right. Enable. Oh, there it is. There it is. A11. Okay, so that tells us that everything that generates the direction signal on the original MDA card does come directly from the ISA bus. Now what this means is that the enable pin, pin 19, that's this data gate on sheet 3. And that data gate signal, which is around here on this sheet 3 somewhere, is what turns that chip off anytime it shouldn't be writing to the ISA bus.
While editing the video, I just noticed it wasn't super clear here. What I'm saying is that those signals that go into the gates that drive that direction signal aren't taking into account if the access is specifically for the MDA card, so the printer port or the video side of things. That means that that direction pin will toggle even if some other ISA card in the system is being requested to write from the bus. So on the MDA card from IBM, what it's using is the enable pin to disable the LS245 anytime that this card is not being selected. The only time the MDA card is writing to the ISA bus is when it is being selected. In other words, you are talking to one of its IO ports or you're talking to its memory locations. I'm looking at the schematics hoping that this Twinhead card works in a similar fashion, but there's no guarantee that that's the case. This can work in a totally different way. As an example, the direction pin on the Twinhead Twinhead card could be configured to only swap the direction around of the LS245 when the card is also being selected. In other words, the computer is trying to read from the I/O addresses or its memory locations, and it could leave the enable pin enabled all the time, since normally the enable pin is only allowing the LS245 to copy from the ISA bus into the card, which is totally harmless to have that on all the time. When you're designing a circuit, there's just many different ways you can do the exact same thing.
And looking at sheet 3, I don't see that data gate output going to sheet 6. There's X-act going to sheet 6 and a write enable signal that goes to sheet 6. So looking at sheet 6 again, there's sheet 3 sends this signal as X-act. We saw that. And there's that write signal. That also goes to here. So we saw those two signals. So where is freaking data gate? Ah, there it is. Data gate goes to sheet 6, comes from sheet 4. Did I misread that? Let's look again. Data gate, sheet 3. Ah, typos in the IBM schematics. Sheesh. I'm only looking this up right now just to kind of get a feeling for how these signals should work on the IBM card, hoping that they're similar on this card. Okay, so I think what I'm going to do is I'm going to stop the camera and I'm going to try to reverse engineer a little bit of that circuit right now just to speed this up, because this video is going to take way too long otherwise. All right, that took a while, but I sort of figured out some of this stuff. So we already knew the LS245 direction pin went to the LS04. I couldn't remember if it was pin 8 or 9, but it doesn't really matter because the input of that is coming from this LS00. This is a Nand gate that's on pin 11, and we never saw that change. And I traced out the two inputs that go to the Nand gate, and unfortunately, one of them is that large 40-pin Twinhead IC. And the other one, though, does go to this LS32, and one of those lines goes to the I/O read line, and then the other one goes up to an LS125 on pin 10. So let's go about these various signals on these pins at least. I guess we can look at pin 30 on the Twinhead chip, see if that does anything. All right, so we're going to start on the LS00, the Nand gate, pin 11. This is one we already looked at. I think it's just going to be low all the time, and that's what we expect. Now, its input on pin 13 is going to pin 30 on the Twinhead IC. It's high all the time. Okay, so yeah, it matches what we saw. So there's not like a break in the trace or something like that, because it could easily be a physical problem on the board where the signal's not getting from the Twinhead chip to that IC. All right, next up is the output of this LS32. Okay, we need to look at the data sheet to see what the truth table should be for the LS32. I don't remember off the top of my head. So that gate has two input signals. This is one of them. This is pin 5. This is the one that's going to the I/O pin on the ISA bus. Okay, there are occasional reads from the I/O port. So anytime the CPU tries to read from an I/O port, we'll get triggers anytime it's actually reading. Okay, so we need to look at the truth table to see what this chip is doing, but we are getting occasional I/O reads. And then pin 4 is the other pin on that gate. And I hit reset. Hey, we're getting a bunch of pulses as well. Now here's the LS32 on the MDA schematic, and it's hooked up to the address enable and the I/O read. I didn't go, oh yeah, I did. I figured out that pin 4 goes to this LS125. I didn't go any further than that. We need to take a look at the truth table to see if the output of this should ever toggle. I think that's an OR gate based on the symbol. Yeah, quad 2 input positive OR gate. So the output of that gate is always going to be high unless both inputs are low at the same time. And if we look at pin 4 to hit reset, we see occasional pulses. And when we look at pin 5, we also see pulses. But it would need to happen at exactly the same time for this chip to actually toggle its output low. And its output is that one, and that's always high. And hit reset, yeah, and it never changes. All right, so let's use the 2-channel oscilloscope to see if these both go low at the same time. I'm assuming they do not. So, yep, indeed they do not. We reset the system again. So we see occasional pulses on the yellow trace, and then we see stuff happening on the red trace, and they're never happening at the same time though. Let's switch the triggering to channel 2. So you can see all sorts of stuff happening there. And we'd be looking for the red trace to go down at the same time. And we're certainly, doesn't look like we're ever seeing that. All right, so what that tells us is, at least based on the truth table we're looking at, this chip appears to be working properly as well. Now going back to this LS125 that feeds one of the inputs of the gates on there, well, that could be problematic as well. But ultimately we could just keep going forever and ever and ever to try to trace the problem, when unfortunately we know that this chip, that little marked pin there, also feeds one of the gates there, and we never see any activity on that. And this could easily be our problem. Now what I didn't do, and probably a good idea to do that, is just check to see if anything is super hot. So far, everything feels pretty normal. The system is currently running, it's on. But yeah, everything is fine. Now remember earlier I took out this PAL, and that didn't seem to make any difference on the board at all. It still was having the exact same behavior. So my thinking is that this IC, the 6040G3, is handling all the chip select and a bunch of other combinational logic on this board. So I'm not quite ready to call it yet on this board. Thinking about how these cards need to work, there's that signal on the ISA bus called memory read. And anytime that is asserted, that is when the CPU in the computer is trying to read from the RAM, the memory. And it might be worth looking to see where that pin is on the ISA bus. I think it's on the backside, and what chip that goes into. If it goes directly into the Twinhead chip, then I think that pretty much is going to confirm that this chip is bad. But on the other hand, this chip may rely on some of these other logic chips for, say, address bus, latching, things like that. It's just hard to say without the schematics. It would take a very long time to reverse engineer. We'd have to remove every single chip on here because there's a lot of traces that run underneath these chips. And unfortunately, it may not quite be worth it to do that much work. But at the minimum, let's try to figure out where that mem read signal is and see what that goes through. This finger right here, that is mem read. That is mem write. That means anytime the system is trying to write to the memory, that line is toggled, and then that's mem read. Let's try to figure out where mem read is going. You know, part of me thinks that it probably goes straight into this Twinhead IC. Let's make sure those probes are set up. They are. Oh, it doesn't. It goes into something else first. So if you don't have the brush probe, this is another way you can try to find where it's going. You need to have a multimeter with a continuity mode that latches quickly enough so you can run over all the pins like this. There it is. It's way up here. And is that chip one of the ones we've looked at before? It is. This is the LS32. That's just a different gate. That's this IC right there. So the mem read signal goes into pin 13 on the LS32. And we can see that's one of the two gates that go into it. Also, pin 12 goes into it, and the output is pin 11. Okay, hold on a second. I was just toning things out. And it's possible that this is not our problem. So that pin I had already marked, that's the one that I found over here on the LS00, and it always looked low. Now the thing is, I thought the output was coming from this Twinhead chip, but I don't think that's necessarily the case, because this is the LS32 that's in question that we are trying to trace the memory read or mem-r signal from the ISA bus, right? It goes into pin 13, there's pin 12, and then the output is pin 11. Well, it turns out that pin 11 also goes to pin 30. So this is the output of that gate. And there it is on pin 30 on the Twinhead chip. So again, if we take a look at that and we look down here, there it is. That signal is on that chip as well. And that was the signal that's never changing. And we know for sure that that MR signal, that's going to be changing. We haven't looked at it yet, but we're going to look at that in a second. So I think we need to scope the inputs to this and its output, because we know the output is stuck. We need to look at the two inputs on here and see if the truth table is ever satisfied. That would generate the change in the output on pin 11. So we can be pretty much sure that one of these two inputs on the gate is going to be toggling, because that's the ISA bus. But the other one, that's that pin 12 that I have on this post-it note. We haven't looked at where that comes from yet. I'm probably going to have to find out where that signal is coming from and see what's generating that, because that might be what's stuck. Okay, I'm on pin 11. That's what's going to that pin 30 on the Twinhead, and we don't see a change there. Yeah, we saw that little sawtooth waveform. Now, when I look at pin 13, that's the MR signal. We're going to see a ton of activity, I bet, on this when I reset the computer. Yep, okay, tons and tons of activity. That's coming from the ISA bus, totally expected. Now, pin 12, on the other hand, that's just high. That's just staying high. Oh, and then it goes low. Okay, but I think when it goes low is probably when the computer's stuck. And at that point, the MR signal is not going low anymore. Because remember, they both have to go low at the same time for this to work. So both probes are connected, pin 12 and 13 on the LS32. So there's all the activity we're getting on the MR signal. So again, I don't think they're both happening at the same time. Let's reset the machine. I don't think they're both happening at the same time. Both yellow and red trace need to go low together. Nah, they don't appear to do that. Right, so it looks like pin 12 goes to that pin on this IC. This is a 125, and I think we've already looked at that chip because I have a little dash on it. But I could see the trace also comes down here somewhere. So it also goes somewhere else for sure. There we go, it goes to that pin as well. So it goes to multiple things. Well, it looks like it goes to this via, which makes its way somewhere else on the board over there. So this signal is coming from all sorts of things. I should make sure that it's not coming from the ISA bus directly, because most likely one of these chips on the board is generating that signal and the other things are just, you know, receiving that signal for its gate. So we have an LSO3 that's going there and here. Okay, so what I said was a 74 LSO3 is actually an LS30, which is an 8-input positive NAND gate. All inputs are high, you get low. Any other input is low, you get high out of it. Okay, so let's take a look at what we're getting. We're looking at the red trace. So one or more inputs are low, output is high. And then it goes low, remember, once the computer halts. If I hit the reset button, it goes back to high again. All right, so there's the output, and the inputs are 1 through 6, 11, and 12. Okay, starting on pin 1, when I hit reset, there's a little bit of activity. And then that's pin 2, lots of activity. 3, stuff happening. 4 is just high. Oh, it has an occasional low there. Same thing on 5 and 6. Huh. Well, 6 is interesting because it's sort of, oh, there we go. I wanted to see some activity on all the inputs. That's certainly noisy. Oh, look at that. Doesn't that line look strangely different than the rest? Okay, so yeah, some of these lines look weird. Like that one looks normal. Now I'm on pin 6. Yeah, it's kind of, I mean, we see activity on it, but why is it noisy like that occasionally? And then those weird sawtooth waveforms? Now I'm on pin 11. That one just seems to be tied to 5 volts. And so does pin 12. So it seems like 1 through 6, these pins down here are the only ones that are actually hooked up to anything. So the truth table says when all inputs are high, then the output becomes low. And it looks like 12 and 11 are tied permanently to 5 volts. And currently the output is low. So that means that all the inputs on this chip should be high. And that's pin 2, pin 1, that's 3, 4, yep, 5, and 6. Yeah, I don't know what this chip is supposed to be doing, but it does appear to be working properly. Only goes low once everything is high, like it is probably right now. And yep, it is. And if I hit reset, it's gonna go high. That's because there's all sorts of activity happening on this chip right now. So that's the chip right there. You can see that one of the traces goes down somewhere. These are the pins we were looking at, right? These 6 pins. Those are the relevant ones. The other 2 that are over here just seem to be tied permanently to 5 volts. Yeah, it looks like those 2 pins, those are tied permanently to 5 volts as suspected. So really it's just these input pins on the top row that are relevant. And we can see a couple of them have traces we can follow. Those 2. You know what? This is going directly to the ISA bus, these input pins. Not all of them, but some of them are. This is one of the address lines for sure. And this one, yep. And this one, yep. So pins 4, 5, and 6 are going directly to the ISA bus, but 1, 2, and 3 are not. So again, this must have something to do with the chip select logic or the select logic for the RAM. So it's mapping the memory into the address space of the IBM PC. I am possibly getting closer to the problem, but I also may not be. I might be on a wild goose chase and I'm going down the wrong path entirely. Looks like pin 1 makes its way over to this chip, which we've already been looking at, the 00 chip. Pin 2 also goes there. Pin 3 goes somewhere else though. The thing that's difficult is we saw activity on all of the inputs to this IC. I know I don't need to worry about pins 4, 5, and 6. Those go to the ISA bus directly, and obviously we don't have a problem there. It's 1, 2, and 3 that could possibly be our issue. Yeah, it seems like everything's fine. All these signals look completely good. I would expect to see something that just looks totally wrong. That's pin 2, and now we're on pin 3. Those signals look perfect. So I did a quick search just to see where the MDA RAM exists on a PC, and it starts at B0000. And doing a little conversion with the calculator from B0FFFF, which is the top of the address space, and putting that in a notepad here, I just wanted to see which address lines are relevant for when the RAM on this card needs to be selected. So we can ignore all this bottom stuff. What's really relevant are these bits at the top. And in fact, I'm thinking that all of the address space from B00000 to BFFFF is mapped to the card. And that means that the only relevant bits are actually these right here, 1011. Anytime the address bus is set to 1011 and it's not trying to do an IO read, it's trying to do a memory read, that's when this chip enable line should be selected. So this chip will output a low when all the inputs are high. Okay, so I'm mapping out the pins on that LS30, what they're going to. So it's 4, 5, and 6 that go to the ISA bus. 4 goes to A16. That should be 1 when this is selected. 5 goes to A17, that's also 1, and 6 goes to A19, that's 1 as well. So that address line needs to be inverted before it goes to this chip. So pin 1 on the LS30 goes down here to this IC, the LS00 that we've been looking at already a bunch of times, pin 7, and then pin 2 goes to that same chip on pin 3, and then pin 3 goes to an LS04 pin 10, and it's this chip right here, and this we've looked at this one already before as well. I'm pretty sure that's an inverter, and this LS04 is a hex inverter, and the other side of that gate goes to address line 18. So that completes what we're looking for from the address line perspective, 1011 or 1101, depending which way you read it. So that's these 4 pins, 3, 4, 5, 6. Those are going to be satisfied correctly anytime the ISA bus tries to go to those addresses. But now we got to go look at this NAND gate, the one we've already looked at a bunch of times down here, see what pin 7 and pin 3 are going to. It's kind of never ending, isn't it? So I just went and had some dinner, and while I was eating, I was thinking about the problem that this thing is having. And what's weird is that when the card is installed, the system freezes. It won't get past that D error code on the post analyzer card. And yet when the card's not installed at all, of course, the system can get past there. So one would think if you were trying to read from that part of the memory, which is sort of the path I've been going down, thinking that that's the problem, well, when the card's not installed, obviously you can't read from that part of memory, or you're just kind of going to get some junk back. So there's got to be some kind of signal that the card sends over the bus that tells the computer, you need to wait for me to get the memory request ready and put it on the bus so you can read it. Think of it like a wait state indicator, something like if you have a very slow card, it needs several cycles to get whatever you're reading from it ready. There's got to be something on the ISA bus that tells the computer to wait. And now I think about it, it almost feels like that is the problem. All that stuff I was doing before, trying to figure out if the chip enable direction signal was good or bad, I don't know if that's necessarily the problem. And I was thinking one method for maybe testing this is putting this card in the system, the CGA card in the system, and booting with this card out so that this won't freeze the computer, getting booted up into DOS and plugging this card in while the system is running, hot plugging it, and then trying to read from memory on this card using debug. I want to see what happens. Can we then read and write from the memory on here? And if we could check the direction signal on this chip, see if it's actually toggling or not, or I don't know. So let's try that. So I'm going to put the CGA card in. Let me make sure the system actually boots. Well, I do have the post analyzer card there. You can just see it at the top of the frame. This gets past the D, system is booting, there's the B. Okay, there we go, it's booting, no problem. So now with this card in there, I need to pull it out of the slot in a way where it's lined up already, but not inserted all the way. So you see it's not in the computer. I'm gonna turn it on. And once it gets past that section on the post analyzer, there we go, we got a beep. I'm gonna insert the card. Okay, it's in there. And the system is still booting, as you can see. I didn't crash it or anything like that, but we've bypassed the part that was stuck. So display switching incorrect. Okay, that's odd. So it's like maybe seeing that this is there or something. I don't know. Okay, so we run debug, and if we want to look at memory, so let's look at part of memory. So this is like the C0000. There it is. I can't remember where the CGA memory is. Let's look that up real quick. According to Google, it's at B800. So remember, the MDA card is B0000 all the way to 7FF. And it looks like CGA is B800. So I think what we see there is just part of the text mode. And I think if I write to part of that, it'll actually change one of the characters on the screen right now. All right, so let's try reading now from the MDA card, which we know is at B000. The address space is that. We're going to be reading from the monochrome card itself. Let's see what happens. Well, it just froze. So I'm assuming whatever's at play that causes this to freeze up during the boot process is exactly the same thing that's happening right here in debug. Can I even hit Control Delete? I cannot. Now it is my assumption if we pop this card out right now, it will unfreeze. Let's just do it. Here we go. I'm going to move this little plastic thing here. Boop. Ah, look at that. So yes, whatever signal this card is sending to the ISA bus is keeping it from being able to read from the memory, and it just hangs. It does a physical hang, which is definitely what's causing it to freeze up at boot. And pulling the card out, that signal goes away and it just displayed all Fs, which is what happens when you display part of memory or the ISA bus that doesn't exist. Okay, so I just filled part of the video memory buffer with 33 and 33. Now the way CGA works is there's an attribute bit for like the color and stuff like that, and then there's a character, and that's why it has a color up there. And I think one allows us to fill more. Yes, okay, so we can tell it how much we want to fill. So like that cleared the whole screen. I mean, I just wanted to make sure I could write to memory properly. I guess what I should do is put this card back in and see if I could write to the memory. I'm assuming you can. It's just I can't read from it, right? I'm just going to do this while the system is running. There we go. I just plugged it in. Feels wrong to do that, doesn't it? The computer didn't freeze though. So anyways, so let's do that again with the CGA. Just make sure I have the syntax right. So we're going to fill 100 with, I'm going to do it with 44. So different color. Okay, there we go. So now let's try filling the MDA memory. 144. Oops. Okay, that froze as well. So again, I think that's some kind of a signal that's causing it to freeze. I'm going to pop the card out and it's probably just going to finish. Boop. There we go. We got our prompt back. So a quick Google search brought me to this ISA thing, the ISA and PC104 bus. This seems to be kind of technical about how it works. So these are all our signals, by the way. So we have the data bus signals, all the address lines, address enable, CH ready, I think it's channel ready, oscillator is like a clock signal, BALE, then IRQ lines, there's another clock line, refresh, there's like DMA stuff mixed in here, and then the IO read and write. That's for reading and write IO ports. Then there's no WS. Is that no wait state? Actually, before I read too much into that, I think I need to see exactly which pins on this side, these are most of the control signals, are actually there because a bunch of them obviously are missing. So the reset line on the bus, which is activated when you reset the computer, that's fed through. There's memory, read and write. We have IO, read and write. None of the DMA stuff is even hooked up. IRQ7 is hooked up. 5 volts and ground. So that's it for this side. IRQ7 is for the printer port. Component side, we have non-maskable interrupt. The finger's there. I'm not sure that actually goes anywhere. I don't think it goes anywhere. All the data lines. There's a signal called ready or RDY. That is hooked up. AEN, I think that's like address latch enable, something like that. All the address lines. That's it. So the only possible signals I'm thinking that could be causing this are this ready line and maybe non-maskable interrupt. Well, that's the non-maskable interrupt. I just look with the loop here, not hooked up. So I really feel like the only possibility is this RDY signal, ready. That absolutely has a trace. So I'm gonna draw on this with a marker. So we know to look for that. So that's the pin, channel ready. The AEN signal address enable. This is asserted when DMAC has control of the bus. This prevents an I/O device from responding to the I/O channel during a DMA transfer. So this is coming from the host computer itself, I think, and is telling the card, don't write to the bus because something else is currently driving the bus. I think that's what that means. So channel ready, here it is, channel ready. Setting this low prevents the default ready timer from timing out. The slave device may then set it high again when it is ready to end its bus cycle. Holding this line low for too long can prevent DMA refresh cycles on some systems. This signal is called I/O channel ready by some references. Channel ready and no wait state should not be used simultaneously. This may cause problems with some bus controllers. What I don't like about this document, by the way, on GitHub, is it doesn't tell us where that signal originates. Does that come from the card or come from the motherboard? But I'm pretty sure, based on the description we read, that it is coming from the card. So I'm going to hook the scope onto this test card here, onto the I/O ready pin. Let's take a look at what that signal looks like. I'll put this into this lower slot. We'll take a look at what that signal looks like with the CGA card inserted. Okay, so it's my assumption when we turn this on, we're going to see pulsing, and we're looking for the yellow trace. Maybe no pulsing, it just stays high all the time. Oh, wait, when the system beeped, it went low. I think we're triggering off the wrong channel. Let's trigger off channel 2. Oh, there we go. Okay, plenty of stuff. Now it's sort of my assumption that as access to this 8-bit video card, the CGA card, it does that. Okay, now it is my assumption when we put this card in, that signal is just going to go low and it's going to stay there permanently. So let's turn this on, or at least it's going to get stuck when it gets to that. Yeah. Okay, so it's stuck at D. That signal is low, and I'm going to pop the card out, and it's going to go high, and the system will keep booting. Yep, as soon as I popped it out, the system booted. Okay, so this card is holding that signal low. I wish I'd thought about the problem before I did all the other troubleshooting, because I wasted a ton of my time, a ton of your time troubleshooting, looking at like how all that stuff worked when I wasn't even on the right track. I always make a big deal about trying to assess the exact problem, what's happening first, before you start doing a bunch of work, because that will help you eliminate parts of the system that are working. And I clearly went down the wrong path by trying to decode the whole memory read signal on this, when I should have seen the clue that when this card was in there, the system couldn't even boot at all. So this is just one of those mistakes that one can make while trying to troubleshoot things you don't fully understand. And I don't know much about the ISA bus. I've never designed a card. Well, I've designed some cards for it, but I never even used that signal to do anything. I just left it alone because the cards I was designing were fast enough to operate without any kind of toggling of that line. But this is an old card, and I suppose it's actually necessary. So what I need to do now is figure out where this line is coming from, why it's stuck low. Well, it's not stuck low all the time. It's just stuck low once the system goes to read from the card here. And maybe what we can do is just figure that out and cut the pin, see what happens without that line being driven at all. But before I do any of that, I just need to find out where it is on the board. Okay, a bit of probing around. I found that it goes to this LS125. And looking at the IBM data sheet for the MDA card, look at that. There's I/O ready. That goes to the ISA slot, and it's on pin 3 of an LS125. It's not on pin 3 on the card, but maybe it's using a similar setup in that it's hooked up to the output of this 74 LS74 for this XACK signal, which I thought has something to do with DMA, which I don't think that line is even connected on this card. Then pin 1 goes to an input on another 74 LS74, and it has an output of a 74 LS08. And what is this chip doing? Seems to be hooked up to this 6845 chip select line, like that's getting stuck, and also an enable signal. Okay, so, and then this pin 1C, let's just follow this, goes to this 7408, which, let's see what it goes to exactly. CPU M cell, okay. Also goes to this gate, 74LS00, goes to an enable signal on sheet 4 and also a chip select signal for a 6845. Interesting. So on this MDA card, the signal comes out of pin 11, that's a Y output. And then these are the two related input pins on the gate, 13 and 12. The description is these bus buffers feature 3-state outputs that, when enabled, have low impedance characteristics of TTL output with additional drive capability, high logic levels. When disabled, both output transistors are turned off, presenting a high impedance state. Okay, so that makes sense. So when it's off, it's not trying to drive the ISA bus at all. Because remember, this goes into the ISA bus and other cards can try to drive that. So you would not want to pull it high or low and hold it there. Like you wouldn't want to drive it high, because if another card tried to drive it low, it would create a bus conflict. So the outputs are disabled when G is high. So let's take a look at pins 13 and 12 on that chip. Let's just see how they look on the scope. All right, I am on pin 13, which is the red trace. And what will happen is as soon as the system freezes, that red trace is going to go low. There it is. If I hit reset, it goes high. Now, reset does go into this card. So there's probably a flip-flop or something that's maybe driving this. I'm not 100% sure, but it's stuck low right now. Now, A is being passed through to Y. A goes through the Y when this G is low. So right now, if we look at the A signal, it's low, and I hit reset, it's just low. It's stuck low. Well, I think that's the problem right there. I don't think it's this chip. I think it's whatever's generating that signal. Now I'm on pin 11, which is the G signal, the enable signal. And what happens is it's high right now, which means the output of this chip going to the bus is high, and then it gets stuck low. And then there's the output right there, and I hit reset and it goes back to high. And I just can't imagine the A signal should just be low 100% of the time. That signal might just be tied to ground. So we can figure that out using the multimeter. And it was my thought that maybe pin 12 was tied to ground, because that's the A pin, the input. But that is not tied to ground. That goes somewhere else on this card. We're back to our friend again. So the input to this goes to that pin, which is 31 on our large Twinhead IC. Well, that's not good. Again, unless that goes to other things, I should look on every other chip, because again, maybe that's not being generated by that chip. Maybe that's just being used by that chip. So here we go again. Oh yeah, look at that. It's also hooked up to this pin there on the 74LS74. Isn't that very similar to what we saw on the MDA schematic? Okay, I'm gonna mark that pin where it goes there. So that's pin 8 on that IC. And this is a flip-flop. And we have had issues in the past with these flip-flops. So that is Q2 output. And pin 8 has a matched pin 9 output, which is the inverted output. So we should look at that signal with this card installed just to see if we see activity there. This was the same chip, if I recall, that failed on the Plexus. Okay, so we are on the output of the flip-flop Q2. It is low, it is stuck low, and the system freezes because as soon as that other chip starts to drive the bus, what's gonna happen is it just drives it with this signal, which is low all the time. Pin 9 on this flip-flop, on the other hand, let's take a look at this. So it's stuck as well, it's just stuck high. All right, let me try to figure out how this flip-flop works. So those are the outputs, they are both stuck. This one is stuck low, that one's stuck high. And then these are the inputs. PR2, clock 2, D2, and then clear. Okay, so I'm on clear 1, which is weirdly at 3 point something volts. Usually you would think that would be hooked up to like a reset line, but I'm pushing reset, that doesn't do anything at all. So yeah, pin 13. Now I'm on D2. It's also at 3.7 volts, not doing anything. What? That's pin 12, D2, and let's look at this clock 2. It's clock, it's just 2, it's the second unit. Okay, now we're looking at pin 11 at 4 volts. What's happening here? This is not right. This is not right at all. These signals are all stuck. Like you could see when I push the button, the reset button, there's like a bit of attempted activity. And I don't see how these could be stuck and at these weird levels. I think what I need to do is cut one of these input pins to the flip-flop. Well, maybe we should figure out where they're going first. But all three of those lines seem stuck in weird ways. And I'm wondering if this chip has just failed and is holding those at those weird voltage levels. I suppose what I should probably do first before cutting anything is just try to figure out where those signals are going. All right, so this 7404, that's one of the signals. This pin goes up to this 7404 up there, which I think we've looked at these chips already. I think these chips are working. I just don't see how all the inputs are stuck on that one chip. When we look at these other chips, because we've looked at these chips, they're outputting normal voltage levels. I'm really feeling like this chip is our culprit here. So I'm going to just cut one of these pins and we'll reconnect it if we need to. Let's see, it should be disconnected now. It is. Oh, so what's on the card comes from this IC there on that pin. So what we need to do is when the system is running, we need to take a look at the output of that pin, hit the reset button and look, see if the signal levels look normal on there or not, now that it's been cut going into this chip here. Okay, so first things first, we're gonna take a look at the input side of this 74LS74. It's floating now because I've cut that pin. Okay, here we go, let's turn it on. All right, it's floating, it's at 1 point whatever. Okay, fine. Now let's look at the output of this 74LS04. Ah, so that's no better. Huh. I'm back on the schematic for the IBM MDA card, and it was the input that looked like it was stuck, right? And we saw 74LS74, that's what we were looking at. In fact, it was pin 8, same pin, and pin 9 was stuck as well. And I think I just cut pin 12 maybe? No, I didn't. I cut this pin that came from the 74LS04. So this part of the circuit seems to match what's on the card here. So the clear input is actually hooked up to the output on pin 9. Okay, which actually matches exactly how this card is. So the output is going back to the input and also goes to this other cascading 74LS74, which I'm assuming U4, it's the same part actually. So that would imply D, pin 12, is actually hooked up to Q. Okay, hold on a second, that's different. Because I cut pin 11, not pin 12. Yeah, I'm just double checking that I did that. So the circuit on this card does appear to be a little bit different than the MDA card, but it's similar. So these two cascading flip-flops are hooked up together. And notice pin 2, which is the input to that first of the two flip-flops, is also hooked up to the signal which turns on that bus driver for that wait signal. And that's the same on this card. It's mirrored that. So when I take a look at pin 2, if I reset the system, that line goes high. And that's because it's the same signal that's turning on that bus driver. It'll go low. There we go. Now, if we take a look at the other signals that are on this flip-flop, pin 1 is 5 volts. I think that's just 5 volts all the time. See the lines up at the top there. And when we take a look at pin 3, the clock signal, I don't think this signal ever changes or does anything. Yeah, that doesn't do anything at all. So that ends up going up here to a 74LS174. What is this doing? Is this like a delay? This has got to be some kind of a delay. Notice how it's kind of going in a spiral here. Like it comes out of 3, goes into 4, comes out of 4, goes into 5. Some kind of a delay circuit. I don't know. Let's try to find that chip. The only 174 I see is this one. It's possible it's hooked up this way. It's pin 3 is the clock input. Let's see if it's on any of these pins. No. Oh boy. It's coming from this PAL, the clock signal. Oh no. Well, that's disappointing because there's really no way for me to know if this is working or not. Oh no, that's horrible. Well, let's just make sure that it's not going anywhere else. I don't want to be tricked like I did last time. Okay, yep, unfortunately that seems to only be going to that PAL chip, and that's it. So I just resoldered that pin that I cut because I don't think that chip is actually bad. So pin 3, which is that clock signal on that flip-flop, is coming from this PAL chip. I'm going to lift the PAL and I'm going to bend that pin out so we can actually drive it ourselves. I mean, it's still actually technically possible that there's nothing wrong with the PAL, And it's pulling that line high or low. I forgot which it was. So it's that pin there. I have the probe touching the hanging pin, the pin I removed from the socket. Let's turn this on, see if we see anything. Yeah, we're not seeing anything. My computer's frozen. It's not for sure that this chip is bad. It could be the inputs to this chip is bad. But again, without the schematics, it's gonna be really tough. We have no idea what's happening inside that PAL chip. So there's really no way for me to know what signal should be going into that PAL that should result in that particular pin producing a good signal. I mean, this is weird. This is 1.73 volts. What? Another one that's at 1.73? So I'm going to keep resetting the system and just see if we see activity on any of these pins. So some of these pins on this PAL are at like 1.8 volts. Another one at 1.73. I mean, it could be that these are just floating, like the outputs aren't used. I don't know what they're doing exactly with this chip. You know, the fact is that nothing's coming out of that pin. I'm not surprised because nothing really seems to be going into this chip either. I would have expected to see like data bus, address lines, something on here, something. Yeah, every pin on there is either weird voltage or 5 volts. I think, let's do that again with the chip removed. All right, yep, same thing, 1.7, or that one's at ground. Okay, yeah, I mean, this is weird in and of itself. So yeah, all these are sort of at ground actually. That one's at 5 volts. I'm hitting reset in between each one of these, just so the system starts executing and starts doing stuff. The mystery continues. I'm not going to necessarily blame this PAL quite yet, because something strange is going on. I really would expect to see stuff and activity happening on the pins going to the PAL, and we're not. So here's the data sheet from the PAL. Programmable replacement for a high-speed TTL logic. Yes, we know that. Power up reset. So the 16R8 is what we're dealing with. And note 1 is clock, and note 2 is output enable. And then there are outputs on notes 3 through 10. So 3 through 10 are outputs, which makes sense because the signal that we're looking for to enable this other chip, the flip-flop, is coming from pin 13, I think. Okay, so pin 11 is the output enable pin. Is that just tied, probably tied to ground, I assume? Yep, tied to ground. Okay, so that's saying that all the pins on the output should be turned on all the time. And then note 1 is the clock, which is pin 1. I mean, we didn't see anything happening on any of these pins, nothing. So where's pin 1 coming from? Let's find it. Okay, there it is. It's this chip here, the 166 that's right above it. I should just go through and find it, see if it's anywhere else too. Oh, there it is as well. That's another 166. I mean, my assumption on these 166s is that's an input. So the 166s are shift registers. Shift registers definitely need to have a clock. Clock is pin 7 according to the data sheet. 166, 1, 2, 3, 4, 5, 6, 7. Yeah, I think it was this pin. That was the pin, I think. So 1, 2, 3, 4, 5, 6. Clock inhibit on the data sheet for the 166. It says pin 6 is clock inhibit. So that clock inhibit pin on both of these is hooked up to the clock pin on the PAL. But what I can be 100% sure of is that that clock inhibit pin on these 166s is an input. And I'm quite sure that the clock signal on the PAL is an input. It's got to be coming from something on this board, and I've missed it. All right, well, it's also coming from the Twinhead IC. Huh. Part of me has me wondering if this Twinhead IC has something to do with generating the clocks on this. There is a crystal oscillator down there in the corner. Wonder where that goes to. Looks like it goes to these passive components here. Yeah, I can't quite tell where that goes to, but I'm wondering if this chip is somehow taking the clock and generating some signals that aren't being generated that go to that IC. using this master clock, 16 megahertz. What we haven't done is look around this chip for a 16 megahertz signal. So maybe that's what we should do with the scope. Let's take a look at everything on this chip. There's definitely stuff that's weird. You know what? Okay, hold on a second. What if there's no clock? What if there's no clock? Okay, we do have a clock. You know, like, what if this is just because the clock is dead, but there it is, it's running at 15.9 megahertz. That's right on the crystal. So we do have a clock. Okay, so that begs the question, does the clock make its way to the Twinhead IC? Maybe it's not getting to it. I mean, I'm not following my rules ever. You need a clock for a system to function, right? As my assumption, we should see some activity on this chip, or clock, or something. I'm resetting the computer periodically, so it's not hung and frozen. We are not seeing anything so far. Just a whole lot of nothing. Okay, finally a pin on the Twinhead IC that's doing something. I'm assuming this will just stop once the computer freezes. Yep, there it's frozen. Okay, hit reset, it comes back. These must be data lines, because I think there's 8 of them. Okay. No clock, though. Where does this clock go exactly? Okay, there's the clock down on an IC that's near the crystal. So it's a 74LS04, and it's got the clock on several pins. It's probably shaping it. But I find it odd that the clock signal never makes its way to this big Twinhead IC or to the PAL. I bet you it's going to be found on the 6845. Well, according to the datasheet, clock's on pin 21. Clock is not there. There's nothing there at all. And on the MDA card, clock on pin 21 goes where? C clock on sheet 3. Okay, C clock, there's 2 of them. 74LS04. And an LS02. Look how this is related. This clock is related to the flip-flop clocks, or at least one of them. U2. Right, we're not getting anything on that clock at all. And that seems to clock all sorts of things, including the 74LS174, this loop thing, which the PAL seems to replace. It probably replaces a bunch of this logic here. But the clock signal there, which feeds all sorts of things, is not working. And that comes out of this. Is that a divider, clock divider or something? Yeah, there it is, 16.2 megahertz. Goes into this 153. And I think this does some kind of dividing or something like that. Is there a 153 on this board? Is that our problem the entire freaking time? Yeah, we have a couple 153s there. Actually, 3 of them. 4 of them. Let's probe these with the oscilloscope and look for clock signal coming into these. We should see the 16 megahertz on one of them, and the output maybe is missing. Let's just make sure we're going to be able to measure the clock. There it is. Now on the IBM card, it's pin 6 on one of the chips, one of the 153s. But I've gone past pin 6 on all of these chips, and there has not been a clock on any of them. I see activity on some of these chips. It goes away once the system freezes. Now, it looks wide because I'm zoomed way in because I want to see that 16 megahertz clock going into one of these chips. Now, this crystal oscillator seems to go through this IC, at least a few of these pins on the top row. And when we flip this over, definitely appears to be some scratches and things right there. And I'm pretty sure, looks like these are actually hooked up together. Yeah, they are. And they go over here to this via, but it doesn't make it. What? You're kidding me. So that's the clock. No way. Can you see this? These 2 pins are hooked together. We saw the clock on those pins. And it goes over here to this via right there. And I think there's a break. No freaking way. Because I'm getting nothing. But if I go from the pins on that chip to there. Oh. You kidding? No, no, no. No way. No freaking way. All right, we're going to use the Dremel to clear those traces away so we can look at them clearly. Well, it looks like there's a break on that trace, but that's not the one we were just looking at. We were looking at this trace, this lower one. And it doesn't seem like there's actually a break there, but there has to be because I wasn't getting continuity. This one that has a break goes from that via to there. That one has got to be broken. I can just see it now that I've cleared the resist away. It's not broken. I mean, doesn't that look broken right there? But this one here, oh, it's now connected. It 100% wasn't connected before, but I think using the Dremel must have like pushed it back on top of it there. Well, I'm gonna put some flux on there and just coat that with some new solder. So put some flux there. All right, there we go. Just double check one more time. And let's just check these. So that one went to here. That one's good. That was the top one. The bottom one was there to the clock output. There we go, looks fine. And then these two, I don't think they looked broken, but we'll just double check. There to there. Okay, that's all good. Okay. Let's put this PAL back in. Let's bend the pin back carefully. Okay, there we go. Pop that in. Okay, let's take a look at pin 1 going into the PAL. That should be the clock pin. And let's turn on the power. Oh man, there's clock there now. You gotta be kidding me. Oh, and the system posts. The system freaking posts. Okay, so right now we don't see anything. That's because I have the RGB to HDMI connected to the CGA card, and I have a feeling it has defaulted to monochrome. So we're gonna go mode CO80. I'm just blind typing. The system freaking booted. Unfreaking believable. So using debug, that's the CGA buffer, and we can do the same thing again, but we're looking at the monochrome buffer, which is that. And I'm going to use the fill command to fill part of the monochrome buffer, which remember froze last time. And now if we take a look at that same memory space, we should see 33s in there. And we do. And if I unplug RGB to HDMI and we switch to monochrome, and I plug this into the monochrome card, oh yeah, there are the 3s. And it was working. Wow. So if we hit Control Delete, yeah, okay. It's freaking working, and it was just a bad trace the whole time, which shocks me. How could it be a bad trace? Because this card was installed in a computer, and it must have worked at some point, but there was a bunch of little scratches on the back there you saw when I zoomed up on it, but I didn't create those. I took the card out carefully. We took a look at it on the bench. I tested it, bench tested it, it didn't work. I just put it aside and it was sitting over on my to fix shelf over there, which has foam and everything. So it wasn't stacked on top of other cards, getting all scratched up. That kind of damage happens when you either stack the cards, a whole bunch of them together, or, you know, I don't know, some kind of trauma that I just don't see how it could have experienced. Not in my handling, at least. Now I just switched over to the Hercules profile, which might be working a little bit better. Yes, it looks perfect. It looks freaking perfect. Wow. The fact that the cursor is offset, by the way, that comes from the fact I'm running like a Xansi, Z-ANSI. It does that. Let's run vid test here, which would generate some test patterns. And okay, it's shifted over slightly. You know, every Hercules card is just ever so slightly different. There we go, looks perfect now. Wow. All right, so I have a few pictures here that are Hercules pictures. I created these using GIMP, so they're nicely dithered and everything. Correct aspect ratio and whatnot. These are photographs that I took, and yeah, it looks perfect. So there's nothing wrong with this card at all. Every single chip on here is fine. The PAL is fine. The Twinhead IC is fine. The RAM is fine. It's all fine. Here's a photograph of the steel bridge looking perfect in Hercules mode. This looks great. If you plug a monitor into this thing, like a IBM MDA monitor, it looks great. All this pixel display on that nice fuzzy CRT. And there's a picture of an ATI graphics solution card being displayed on a Hercules card. Both that card in the picture there and the one, of course, on the bench have now been freaking repaired. Well, the final thing to do on this card is to basically take away the bad. I wrote there with a Sharpie. Luckily, that just comes off very easily. And what this card is going to get now is a tick mark to say that it's freaking good. No longer bad. All right, well, that is going to be it for this video on repairing this video card. I thought I might get to the floppy drive if this was an easy repair, but I ended up getting quite stumped. The funny thing is that I always talk about the things you need for something to work, usually in the context of a computer, but I say you need 5 volts, you need clock, and you need a reset signal. Did I follow my own advice with this card? No, I totally did not. In fact, as you just saw, I went off on a tangent thinking that it was something to do with the memory write stuff, or memory read that is, and we reverse engineered a whole bunch of the card to try to figure out if that signal was working properly. But I was totally chasing my tail and I took the wrong approach because I ignored my other thing that I say you need to do when you're trying to fix something is once you validated the basic stuff works, then you need to look at what exactly is wrong. I mean, exactly is wrong. What are the exact symptoms? And I was not following my own advice there either, because as you saw, when this was in the computer, it would freeze, but when it was not in the computer, it would not freeze. And with a little ISA hot swapping, yes, I mean, you can do it, just don't short the pins together. We figured out that anytime I tried to access this card in the memory space, it would just freeze the entire computer. So that led me down the whole thing of trying to figure out what signal on the ISA bus would do that. And we reverse engineered all of that to then get to the fact that that stuff was coming from the PAL. But then the PAL, once we looked at the data sheet, we know that it needed a clock to run and there was no clock. And then we saw the clock was working and, you know, we got there. You just watched the video. In real time, this has taken me many hours to get to the solution. Although you notice I haven't changed clothes, it has been the same day that I've done all of this. So hopefully I can edit this video together into something interesting and there's some lessons to be learned. For me personally, there's definitely lessons to be learned. Always check for the clock on anything that has its own crystal oscillator. Make sure the clock is working. Because I think if I had done that from the very beginning, we'd done a little bit of tracing and maybe looking at the CRTC, which I knew already needed a clock, I would have seen it had no clock. And then I could have fixed this thing much more quickly. So there you go. Even I get stuck sometimes and go down the wrong path and multiple times down the wrong path. It's just how it goes. But it does make it very satisfying when I honestly was ready to give up on this a couple times. I was like, oh, so the Twinhead chip is bad. Oh, okay, well, maybe not. Oh, the PAL is bad. Oh, okay, well, maybe not. And then I finally got to the bottom of it, and I mean, just think it was physical damage. I mean, how ridiculous is that? Physical damage. I kind of saw a few of those scratches when I was looking around the back of the board, but I'm like, nah, they don't look that bad. It couldn't be that bad. But just like that Laser 200, they didn't look that bad, but they were bad enough to cause the computer to not work, and that was the only thing wrong with Laser 200, just like it was the only thing wrong with this. Hope you liked this video. Hope you learned something. I certainly did. If you enjoyed this video, I'd appreciate a thumbs up, but if you didn't, you know what to do. Huge thanks to my supporters. Names are going up beside the screen. They make it possible to do this full time. Subscribe, YouTube, thumbs up, all the usual engagement stuff. Really does help me out. It's wild to watch videos that have a lot of engagement, as in lots of comments, and the ZX81 video I did recently is a perfect example of that. Lots of comments, and it pushed that video up to the rankings of my #1 video in the last 10, and that's simply because I think a lot of people were commenting saying, oh, this is great. So it's funny that those interactions, whether you give it a thumbs up or you give it a comment or whatever, any interaction like that, even a thumbs down, helps promote the video. Plus watching, I mean, who knows? I don't understand how it all works. People think they understand how YouTube works, and I don't know. I certainly don't, but I just saw the weirdness of that video doing really well, And I think a lot of comments were what really pushed it up. So anyhow, that's going to be it. Thanks very much for watching. Stay healthy, stay safe. I'll see you next time. Bye.